and my partner in crime is Stephen Loftus Mercer. And we're going to talk to you about something that we've actually been working on for quite a while. Channels, formerly known as asynchronous wires, are now available as first-class elements in LabVIEW 2016. And so we'll have a brief description of the history and what we're producing in 2016. So a philosophy that we've had in LabVIEW since the beginning is reducing artificial complexity. And a task is inherently complex due to the nature of what you're trying to accomplish, and it's artificially complex because of the tools you have to use. More powerful tools reduce the artificial complexity and therefore the overall complexity of the task. So our original goal was to make a tool for scientists and engineers that would be as productive as a spreadsheet was for financial analysts. You've heard that many times perhaps. And I think we succeeded by inventing LabVIEW with this graphical structured Dataflow programming language. And we've been fleshing out the capabilities ever since for the past 30 years. Well, one capability we knew that wasn't addressed well at the start was the ability to communicate between parallel loops. Over the years, we've introduced a variety of ways to accomplish this using stateful sub-VIs or references or globals or Q references. But none of these were really satisfactory because they didn't visually show the flow of data. And all of those mechanisms, global and references, are kind of antithetical to data flow. So I started about a decade ago experimenting with what I called at the time asynchronous wires. And now we finally productized it and have it available in 2016 under, I think, a much better name of channels or channel wires. So compared to previous state-of-the-art in LabVIEW, channels really greatly reduce the artificial complexity of communication between parallel loops. The communication is much easier to understand because channels visually show the by-value flow of data from one loop to another and abstract away the details of synchronization and initialization, shutdown, cleanup, and so on. So a channel is distinguished from a regular wire by its drawing style. Invisible tunnels, flanges of the sub-VI calls, suggestive of a pipe or a pneumatic tube. So the difference is subtle, but it's easily recognizable with a little bit of use. We started out with something a lot more in your face graphically, but found that it was much more noisy on the diagram than it needed to be. So, how do you create a channel? So if you pop up on any terminal, you can select Create Channel Writer to get a dialog box. And you select the kind of channel you want and the kind of endpoint you want for that channel. Click OK, and then the endpoint is dropped and wired up. The first time a particular channel is created, it might take a few seconds for it to actually script the instance in the background, but thereafter it will drop very quickly. So on the left side of the dialog box, you can see the principal channels of stream, tag, and messenger, and at the top of the window. And below are some additional channels, accumulator tag, and 3 variations of stream that are more specialized. And I won't talk about them today, but when you get 2016, you can play with them if you like. And then on the right side of the top of the dialog box, there's various endpoints available for a particular channel. These endpoints are all fundamentally the same. They take an element in and put it on the channel, or they take an element from a channel and read it out. The difference between the endpoints is with some ancillary parameters that allow you to do provide or extract a little bit more information about the state of the channel. And then at the bottom of the dialog box there's a little animation that suggests the functionality of the channel. And it description of the endpoint. So that animation is something that Stephen figured out how to do, and we think it's going to be popular, and it's going to want to be present in a lot of other situations in LabVIEW. We'll see. So if you pop up on the output of the write endpoint for a channel and select channel reader, you can get a similar dialog box. Select read endpoint. You click OK, and the read endpoint instructor can wind up. So this is not a particularly useful example, of course, but I'm just showing the pop-up menus. If you have a particular endpoint, you can pop up on it and select replace channel endpoint, which will lead to the same dialog box as before, and you can select a different one of the endpoints if you'd like. So, putting it all together, here's an example of a stream channel connecting a producer and a consumer. So, starting with the random number strip chart that we all love as a producer, loop, pop up on the wire, select create channel writer, stream and write are selected, so click OK. Wire the channel over to the consumer loop. Uh-oh. It wasn't right. No. Oh, bummer. How are you going to do it live?
I don't know. See, I can keep it alive.
So the most, I think the most useful channel to find will be the stream, probably followed second by tag. I'll show the stream first. But if we have a producer, loop, and
Who's that being running?
just a random number strip chart. Select stream right.
This is that couple seconds pause you're talking about?
Yes, it's scripting the instance of the channel for that data type on this machine and then wiring up. If I wire the channel over to a consumer loop, it's going to pop up and create a reader. Then
First time LabVIEW's never been used on this machine.
So wire that over and then pop up on it to create a reader, and then you can wire that to a display. Just create an indicator. And a button on the other side can be used to set a flag for the last element and terminate the loop. So here's an example of a sideband communication that goes along with the channel. There's a flag on the stream that you can set and indicate that this is the last element being written to the channel. And so that's the clue on the producer side to end the loop. When the consumer loop finally sees the last element, it knows to stop as well. So if the producer gets ahead of the consumer by 1,000 points, and then the producer sends the last element that stops, the consumer is going to continue to read all those 1,000 elements until it catches up, sees the last element, and then stops. So this is a very common scenario for many applications communicating between parallel loops. So we added that sideband to make it particularly convenient for shutting things down normally. So the next example is a tag example. Tag is, so a stream is like a FIFO or a queue, and a tag is like a global. So it's a single element buffer. It can be read and written multiple places. So it's a scoped global in the sense everything that's wired to it can access it and nothing else. So if we create a similar kind of loop and with a tag, and actually you don't want, why not? Here's what you want. Just do a display, and then the stop button is where the wire to the tag. So
Oh, we're going to
just
do that.
Yeah, so
That's easier.
if we had 3 independent loops that weren't actually sharing data, but you wanted to stop them all at the same time, then how would you do that? Well, right now, you might put a button in one loop, or if you had a button in each loop, you have 3 clicks on the front panel in order to stop it, or you have to use a global. But if you use a local reference to the button, then you don't get the mechanical action, and so it is a little bit tedious for turning things off. Well, you can turn things off, multiple loops off, by using a tag. So one loop will have a button in it and set the value of the tag, and then another loop can read it. And
So channel wires cannot enter and leave the same structure because they aren't data flow. So it doesn't make sense for them to pass through a structure node. So that's why I had to do the fork out at the top level.
so what's happening here? We've got one loop with a button in it, and when you hit the button to stop the loop, it writes a true to the tag. And the other loops are running, and eventually, when they get around to read the tag, they'll see a true and know to stop. So they're not synchronized in any other way, they're not sharing any other data, but they can all stop together. And in general, they're running at different rates, they'll have different amounts of data that they process, but they'll all synchronize and stop. So that's another convenient pattern, I guess, that we've seen a lot. So if we go back to the presentation, I can show you a non-trivial example of stream, a multi-stage, multi-rate FIR filter. So if you look at the diagram here, what you see is 2 while loops and 4 sub-VI calls to a re-entrant sub-VI. All of that is running in parallel. And those individual sub-VI calls are doing simple FIR filters, and so this is a multi-stage filter, in this case doing a rate conversion from one sample rate to another sample rate. So each filter stage, each sub-VI call is reading from its input stream and filtering and writing to its output stream. But the number of tokens that it reads on the input versus producing on the output is not, doesn't have to be 1-to-1. And so if you notice the leftmost sub-VI call, it's producing 2 output values for every input value that it's reading. So it's interpolating by a factor of 2. The next one is interpolating by a factor of 2 and decimating by a factor of 3. So these sub-VIs are running at different rates internally. Each sub-VI is basically a loop. So this is showing 6 loops running in parallel with streams of data connecting them.
Let me just really stress that point. Every one of these sub-VIs is running at the same time. The channel wire is not creating a synchronous dependency, so it doesn't have to wait for its upstream. It's saying that these 2 independent pieces of code are in communication. It's a visual connected tissue, not a standard synchronous data flow wire. So I've been trying to test out different phrasing, and the one that I've been told works best is connected tissue. So I don't know why. I used that phrase the last time we presented this, and everyone like, oh, I get it.
So another way I like to think about it is, we've had wires in LabVIEW forever, since day one. Now we have plumbing. So the stream is like plumbing, connecting all of these parallel entities. So if we take a look at what the filter sub-VI is actually doing, there's a bunch of code on the left side of the diagram that's just rearranging coefficients and stuff to make that loop a little bit more computationally efficient. The while loop is producing one output value on its output stream for each iteration, but it can read 0 or more input values using the for loop. And so that's the way I get the difference in the rates from the input and the output. Two parameters, the interpolation and destination factor, basically are telling me for each output I generate how many more inputs do I have to read in order to get enough to filter. So, okay, other pop-ups that are available for channels. Now, if you've got a channel that you've created and decide that you want to change the data type, now you're going to, you see the coercion dot, it's going to convert that to double precision and send it over the channel. But you can pop up on the endpoint and either recreate the same endpoint, or you can say adapt to type, and it will switch over and become a channel for an N32. However, the reader now is trying to read doubles, but the channel is an N32. That's why that is broken. So pop up on the reader side and say adapt, and it will adapt. And of course, you could change your indicator as well. A stream is like a queue, and it connects a single writer to a single reader. So there's only one source and one destination for a queue. However, there are some situations where you might want a producer of data to actually send the data to 2 locations or more locations. And so we have a node that we can drop down and insert in the channel and say replicate. And what this does is it inserts a sub-VI call, which is just a loop reading from the input channel and writing to 2 separate output streams. And so now you can replicate the data and send it to multiple locations. This you probably have to go back to LabVIEW to show. So one of the really neat capabilities of our implementation of channels is the ability to probe the channel. So when you select a probe, we open up a special window with information about the channel. It shows the instantaneous state of the channel, but you can also pause it. And when you pause it, you can see what's in the channel at that moment. Both the producer and the consumer are stalled, and when you single step, you're actually continuing into the next channel operation of read or write. And in this case, you'll see a write come along, and there'll be a value at the front of the queue, and then you'll see read come along and take it away.
This comes as a direct result of so many of you over the years asking me for, when I in-queue data into a queue, I would like to run until that data gets dequeued, and this basically takes care of the long distance single step.
Yeah, so when you're making applications that are communicating, you've got a lot of activity going on, you can actually stop and probe and see what the state of the system is. So I think this will be a big debugging assistance. So let me just quickly go over the endpoints. So for a stream channel, well, for any channel, the simplest endpoints are write and read. And in the case of a stream, we've got write and read. Most endpoints come with a timeout, which defaults to -1, so you wait indefinitely until you're able to proceed with the operation. On the stream channel, there's another input. I'm sorry. On the write and read inputs, there's endpoints. There is a output called count, and that basically is telling you how many elements are in the stream at the time that you've completed that operation. So if you wanted to do some processing to keep from having a big backlog, or you wanted to throttle things, you have some information to be able to do that, and it comes with the endpoint by default. The size input on the right side is what you can use to specify the buffer size for the channel. By default, a stream will come down as unbounded, and so the write will never block. It'll just keep growing the queue. That's not often the kind of behavior you'd like. You might like to bound it, so specifying the size as possible. The size specification is used on the very first call to establish the size of them, and thereafter ignore it. Last element we talked about, a way to sideband channel to communicate that the channel is closing. So the other endpoints, read and write multiple, takes an array of elements in and out, pretty obvious. Write and read schedule is a way to specify a time when you want to read or write. And this is anticipating some future capability that we want to have with timing in order to time I/O and communication, but it's not particularly useful at the moment. And abort is another capability of another sideband channel that works both ways. So a reader or a writer can set an abort flag, and the other endpoint will see it. So a reader can decide that it needs to exit because something has gone horribly wrong, so it can set an abort on the channel, and that will notify the producer to stop as well. So it's another pattern for applications where people want to be able to have some more flexibility in error handling and recovery, but it's more involved than I can go into here. Okay, tag channel endpoints again. Write and read are the simplest. The read timeout normally. The write never blocks because you can just always write the value. The read by default won't block. It'll just read whatever the latest value is. But you can also specify a timeout, in which case the read will wait until that amount of time to give a timeout, or it will return when a new value is available on the tag. So it's a way to not have to busy wait on a change in the tag value.
This allows you to basically use it as a substitute for notifiers, for those of you who are looking at that.
The missed output on the right on the read endpoint basically tells you how many data points you missed. So if it comes back as a 0, it means you've read a value and you didn't miss any. So it's a new value. If it comes back as a positive number, then you missed that many points. You got a new value, but you've missed some number of intermediate runs. If it comes back -1, it means that it's a stale value. It's the same one you saw before. And again, there's a scheduled abort version from the tag. So, how can I tell what's a channel and what's a regular wire? Well, as I mentioned before, there's subtle differences. There's an asymmetric coloring so that it looks a little more three-dimensional, like a pipe or a tube might look like. There's invisible tunnels and flanges at sub the eyes, and these hints will become really obvious very quickly with a little bit of usage, and you'll be able to see where the channels in your application are. Won't channels make diagrams too confusing? Well, actually, I think channels extend the G syntax and actually make things simpler. There's fewer references floating around. You can more easily spot where the sources and the sinks of the data are, where things are flowing. You don't have extraneous code hanging around for initializing, cleaning up, and so on. And the sideband communications really make it a lot easier and safer to make applications, communicating applications.
You notice we also got rid of all those air wires because they're all things that we can actually check internally, so we didn't need them on the channels the way we do on the reference types.
Yeah, there are no errors. If a stream, if a writer can't fit something in the buffer, it will either wait there until it can, or if you put a timeout on it, it'll come back and timeout and say, it was unable to write. So I think it will actually make things a lot simpler. So our channel is going to change data flow as we learned it. Well, I think they're augmenting the data flow that we've already learned with an asynchronous data flow. It's still data flow, it's still by value, so it's much easier to reason about and get correct. And in fact, I think that we probably overuse references, and it's probably something we resort to because we haven't figured out a good by-value representation of it. So it just means that there's still more work to be done. I know how to use the built-in queue. Isn't it sufficient? Well, yes. Channels, in some sense, don't make anything more possible than we could do before. They just make it a lot easier and safer. If you use a queue, you have to initialize it, you have to clean it up, you have to figure out then what kind of additional channel you're going to use in order to synchronize the end and get everything to stop consistently. So, yeah, you could, queues will still be there, globals will still be there, you can still do things the way you've always done them, but I think channels will make it considerably easier. Channels are for beginners. Why should I care about them? Well, I think actually channels could be for beginners. I think that it's an easy enough concept to learn. And in fact, I think it's easier to learn the esoteric about references. But I think they'll help experienced users make applications quicker and easier and safer. You don't have to continually make the same infrastructure to get the communication to work. Now it just works when we connect to multiple loops. So I'll have more to say about that later, I guess. Can I hide channels or all wires except channels? This, I think, is a piece of a much larger request. It would be nice for if we had the ability to show our application at different levels of abstraction. And so it's not just channel wires or non-channel wires that we want to show and hide. It might be whole sections of diagrams, the error handling, special casing, and so on. And so this is an active topic of research for us, is to say how would we solve the more general problem of being able to have levels of abstraction in what we're looking at. Can channels be used in a build application? Yes. What are the performance impacts of channels? So channels are implemented actually using sub-VIs, and they're written to the best of our ability using good in-place techniques, and so we believe them to be the highest performance that we can achieve. We're always aware that there could be bugs that are impacting performance, but as far as we know so far, they are the best performance achievable. Can I bundle channels together? This is interesting. Channels aren't data. They're actually, what did you say?
Connective tissue.
Connective tissue. So you can't bundle those together. That said, we also realize that if you've got multiple channels running from one section of code to another section of code, it would be nice to have some kind of a way to group them together. And but again, that's a research topic for us. We recognize the value of being able to do that, but we haven't figured it out yet.
If you hear Jeff or I or anyone else on the LabVIEW R&D team talk about zip ties, we've been talking about zip tying lots of these cables, these channels together. That's what we're brainstorming about, if you happen to hear one of those conversations.
That's right.
But syntactically, it's a bundle and bundle, right?
Yeah, we'll take it offline.
Yeah, but it's not.
Yeah, syntactically, yes. Semantically, not at all.
Yeah.
Right, right. What happens if two nodes are connected by both a regular LabVIEW wire and a channel? That's probably not a good idea. The wire means sequential execution. Start the second loop after the first one is completed. A channel means I'm expecting both loops to run in parallel so I can transfer data between them. So it's a semantic error of the first order, and it would likely deadlock. Now, we ought to be able to have the compiler recognize if you make a mistake like that and give you instant feedback at edit time. And again, we're working on that. That's a future research project, but we could do a lot better to provide some of that kind of feedback. When do we use a tag versus a string? Well, it depends, but use a tag when you're thinking of using a global, and use a stream when you're thinking about using a queue. What's a global?
Good user. His question is, what's a global?
And for me, it's my worst mistake. What's the biggest drawback of channels? So this one, I think, is interesting. It's going to be easier to construct communicating parallel loops and applications with multiple actors that are communicating. But that doesn't mean that the application itself is easier. I mean, parallel programming is a challenge. You have to think about a lot of things to ensure that there isn't deadlock, that things are being handled expeditiously, and so on. And so this won't make your entire application easy. That's still going to require some good thinking about how to arrange the communication. It's going to make all the boilerplate, all the infrastructure, and it's going to make that part easier. And it's going to make it safer because certain things like these sideband channels are going to eliminate a lot of opportunities for deadlock. So I think what we're going to see is that people will hit up against the interesting and challenging issues of parallel applications rather than the syntactic and infrastructure problems. And so it'll be interesting to see what happens though.
So since we have LabVIEW here, we didn't have a finished version of it the last time we showed this presentation. I want to make sure everybody is aware. If you go into the examples directory of LabVIEW, and go here to channels, we have got a whole list of shipping examples here that show off not just, so your basics is an actual tutorial for learning how to do this, walking through just the basic things. There's a demo for each one of the specialized channel types. There's some entire application development processes. There's some very advanced programming that any of you who are language theorists, I really want you to look at and give you some feedback and discussion about. There's the the data processing stuff that Jeff was showing for looking at how to fold this into your measurement applications and your common computing. One thing we didn't put in here, the channels are available on real-time and desktop. They are not on FPGA. That's waiting for 2017, but we'll have them there shortly. And the last thing is, if you want to look at this and more, down on the expo floor, we have at the LabVIEW Pavilion, there's a demo running that'll let you see a whole mass of parallel loops all executing together to create a sort of software Rube Goldberg. And you can see how tight we're able to pack things and how easy it is to figure out who's talking to who, as compared to what the Q representations might be.
So one other channel that we think is going to be very important that I didn't talk about was the messenger channel. This has a hybrid of capabilities of the stream and a tag. There can be multiple readers and writers of the messenger channel, and the data on the channel is a message that you get to define what the contents are, and it's LabVIEW class based, so there are methods that you can have associated with the messages. This is another level more complex and sophisticated than the tag and the stream, and so I figured there wasn't really enough time to go into details about it, but that's another one where we have some good examples to show you.
So, do you have any questions? John?
So the data that's on the messenger channel is on there?
Yeah.
So the data on the messenger channel is not there. However, if you pop up on a string and say, create a messenger channel for it, we will script a new class that contains a string, so it will flow on the messenger channel, but it will come out as a string on the other side. The real power of the messenger channel is when you create a class that inherits from the base class of the message channel and put the information that you want in it. At that point, you have available to you some callbacks in the form of methods on your class that can be used in interesting situations.
Have you been thinking about crossing the executable boundary in the security channel?
The question is, have we thought about crossing executable boundaries? So between EXEs, between desktop and RT and FPGA. Jeff, have we thought about that?
Oh yeah, in fact, that's the next research project Steve and I are going to be working on. We're thinking about being able to cross the boundary to RT, from RT to FPGA, from LabVIEW application to interrupt service routine. There's lots of possibilities that we can imagine, and that's where I think the real value of the channels is, because that's ridiculously hard to do today. And if we can simplify it down as simple as drawing a wire across there, that'll be awesome. So we're looking at that next. Yes. Well, thank you. I really feel exactly the same way. For me, this has been a 30-year quest to try and find a representation that would show by-value transfer of asynchronous data flow that's consistent with the rest of LabVIEW.
You can actually literally think about it. If you think of every write node as throwing data up to the second floor of the house, and every read node as it coming back down from to the first floor, On the second floor, everything is completely Dataflow consistent. And then it comes back down into the normal plane for back to Dataflow.
Brings it to another dimension.
This really makes the parallelism a lot more accessible. Yeah.
And I will point out that, as Jeff mentioned, this is all built out of VIs, so you can drill in and you can take a look at the internals of this. Since it's Alliance Day, I'll mention something we're not going to mention at the user presentation. We built these in G, and you can actually build your own channel. So each channel kind is its own protocol. You know, tags are overwriting, they've got this lossy sort of thing, streams are lossless. You can take ours, clone it, rename it, and then start building your own. There's some whole parts if you start rolling your own, which is why we're not productizing it at this time. But we have documented online at the Channel Wires community forum how we go about doing this, and if you want to ask questions about that sort of advanced, playing around with it, we monitor that forum to answer questions there.
So I wouldn't recommend starting to try and write your own channel out of the gate. I think we've encapsulated in the channels that we've provided a lot of the basic functionality that we've encountered over many years of experience. So I would think you'd be able to get most everything you're looking to do done with the existing channels. But if you have something that is different, we want to know about it.
Yeah, this is a really nice network for doing communication between multiple participants. But how about something like Loftus Drive when you can do runtimes?
So let's go look. Basics lesson 5. So whenever you open a VI for the first time on a new machine, it regenerates the instances that VI uses. If you've got data text that VI hasn't seen before. So we pop this open. What you'll see here is we can call through sub-VIs, just as we saw earlier, but we can also go through the call by reference node. So the channels allow us to express any amount of static communication. And the only place where we get anywhere close to dynamic is that the tag and messenger ones can go through the parallel for loop, where you can spin up an arbitrary number. But by and large, they're static communication. If you want full dynamic, that's why when you would still have to roll back to the ref nodes. But if you've got just static communication, this gets a long way. Yeah, jumping ahead, we skipped lessons 2, 3, and 4. So that was a kind of a, as some of you may know me on the forums as Aristos Q. The Qs have been my baby for 16 years. And I was very concerned about that exact question. The basic stream is not as fast as Qs. It has some capacities and potentials, and it takes care of some edge cases that we burn some processor cycles on. If you come down to the high-speed stream, though, the high-speed stream, as you can tell from the animation, goes a bit faster. And the functionality it provides, under the hood is written with the Qs. It has a little bit of overhead compared to the plain Qs, but that's because I actually took care of some race conditions that are not commonly checked for. And I know this because I get your cars. And I close them as user error. So, but yes, we have pared this down as tight as we can. We obviously will never guarantee that we have gotten every edge of performance, straightened out. This is one of those nice times when it's written as G code. Maybe you'll spot something if you're playing with it. But we've tried as hard as we can. Most of the time, you should be able to use the stream. It's plenty fast. There are some very big edge cases where you would want that last little bit of performance. No, not generally. Anyone else?
I don't know how to, when you're passing the channel in the sub-guides, it looked like you were reading the channel and writing the channel as you had. I mean, how did, I had a hard time wrapping my head around, how does each sub-VI know which data is right and is writing to the channel again?
So remember that all of these are always running. So let's take this
So
view.
internally, they're a loop. So if you inline the sub-VI, you would see a loop that is reading from the input channel, writing to the output channel, has some logic in between. You can collapse all that down to a sub-VI, and it works the same way.
So you think of this bottom diagram here as just sitting on this diagram, because the clone, it's the same clone. It's never, the sub-VI isn't exiting and then being done. It's just ongoing running. And the connective tissue takes care of saying, I'm connecting this clone to this clone.
So to maybe help answer that, if you remember the diagram we had with the FIR filter. So there were 2 loops on the end and 4 sub-VI calls. When that diagram starts, the producer loop starts running and putting things into the first stream. The consumer loop starts running, but as soon as it gets to its read endpoint, it's going to block because there's nothing to read yet. All 4 sub-VI start running, and internally there are loops, and they're trying to read from their inputs, and so they're all blocked as well. As soon as that first value is written on that leftmost stream, then that first sub-VI can start doing its iteration to produce an output token. And so in the steady state, all of these are running in parallel and data is going through all the streams. When the stop button is hit on the leftmost loop, it sends the last element flag, which is recognized by the first sub-VI call, and it stops its loop, and so it completes. And same with the other sub-VIs in loop. And when all of those things complete, then that diagram is done. That's clicking.
Well, I guess I'm just thinking you have all those 4 things are outputting something. It's still on the same channel.
No, it's not. They're each in different channels.
Oh.
Every
So-
wire is a separate channel. There we go.
So, if you think of it as plumbing, sub-VIs are running and stuff is flowing in, and you're reading it an element at a time and producing an element on the output, causing it to flow. But that sub-VI is sitting there running while the reading data and writing data on the channels.
It's actually maybe really helpful to think of this as an FPGA target.
Yes, or also very closely related to our LabVIEW comms package, where you work in a model of computation that is kind of a high-level view of this. All the icons you have there are just stream processing icons, and you wire them up.
Yeah.
So this,
Things like TCP/IP with that, can't you?
Yes. How many of you have done pipeline programming in FPGA?
Exactly that.
This is what this is. This is why we were kind of upset when we didn't get the FPGA ready for 2016. It missed by weeks. We missed the shipping deadline. So, but we'll have it shortly. For us, shortly. No. All right. Well, thank you all for coming. Tell your friends we're going to do this twice more on Wednesday. Thank you.